Oh, it's automatic recording. Awesome. Okay. Yeah, we'll just give it a minute to let people trickle in. Hi, everyone. Yeah. All right, well, thanks for joining, y'all. We'll give it a couple minutes, let people trickle in, finish their lunches, whatever they need to, whatever they need to do. So yeah, I think I'll give it to maybe 103. I think that sounds good. Like give people a couple minutes to come in.
The kids are out of school today in most of Georgia. So I was like, Jewel, I got a presentation. You finna get up out of here. Go call your little boyfriend. Go over there for the day because you can get up out of here. So I dropped her off at 11:30. Bye. You ain't gonna be getting out here. You won't believe how many presentations I had with Jewel and forgot. She came out here and said, Mama. And everybody started laughing. I'm just like, girl. Did I tell you I had a presentation?
Kids, that's hilarious.
She's 17. She don't care.
Yeah, my nibbling 17. They're the same way. All right, let's give it. Oh, guess I'm excited. I was like, let's give it another. It's got another minute, and then we'll go ahead. Go ahead.
You excited to hear about continual learning?
Yes,
Oh my God.
very excited to hear about this. This is like so outside of, what I do and the techniques. I'm like, India's gonna do some really cool stuff, and I'm excited to hear about it. I've never seen you give a talk before, so I'm also
Oh, for real?
so very excited as
We'll
well.
see if you like it.
I'm gonna love it. It's not a matter if I'm gonna like it. I'm gonna love it. I already know.
There's a lot of science mixed in with extreme Atlanta, so we'll see.
Perfect. I think that's a perfect. I'm here for it. Okay. Give it a few more seconds here. Okay. All right, so we'll go ahead and get started. So thanks everyone for joining us. My name is Caprice Phillips. I'm the current vice president for Black in Astro, and I'm really excited today for our very first Black in Astro speaker series with Dr. India Jackson. So before Dr. Jackson speaks, I wanted to introduce her with her bio. So Dr. India Jackson is a trailblazing computational astrophysicist and space weather scientist, notable for being the first Black woman to earn a PhD in physics from Georgia State University. Snaps to you. So her expertise encompasses heliophysics, machine learning, and cloud computing, with a focus on automating image segmentation and object detection for analyzing solar events. India has made significant contributions to NASA through internships at Johnson, Goddard, and Jet Propulsion Labs. Currently, she is a summer postdoctoral fellow at the Frontier Development Lab, where she collaborates with leading AI partners to advance predictive models for space weather. Her work has been showcased at prestigious seminars, including the Harvard-Smithsonian Center for Astrophysics, and she has been honored as a member of Georgia State University's 40 Under 40 class of 2024. So today we're going to hear a talk titled Geo-CLoak, Operational Machine Learning Tool for Global Geomagnetic Field Perturbation Forecasting. I said it right, I think so. I'm super excited for your talk, India. So you go ahead and take it away. And we'll leave the Q&A open at the end to ask Dr. Jackson about questions regarding her work or just career journey or just any information you would like to hear more about at the end. And with that, India, please take it away.
Wow, that was a great opening. I really appreciate it. And I appreciate everybody for coming and listening to the research that I conducted over the summer with the Frontier Development Lab, also in partnership with NASA in Mountain View, California. We use Google Cloud Services and NVIDIA. And my group was about geo effectiveness, and we used continual learning, which is a paradigm under machine learning. So first, let's go over my team, starting with myself. I was the pipelining guru, and I did most of the web hosting production. We'll talk about that a little bit later. And I am a mix of quite a few things. I have degrees in several fields. So I mostly do data analysis, data migration, data manipulation, image segmentation. But I'm also a heliophysicist, and I incorporated some machine learning within this group. We also have, oh, I'm sorry, and I come out of Georgia State University. We also have Opal. She comes out of University of California. She did most of our scientific inquiry this past summer, and she also did some machine learning. She used quantity quantification and interpolation for our ground perturbation measurements. Bubiti is coming out of Colorado. He is a postdoc at University of Colorado. He did quite a bit of the data deployment and getting the data ready to input into our machine learning models. We have a couple of them, and he's also a heliophysicist. And Chetrich is a PhD candidate at Georgia State University. We both are in the GSU data mining lab, which uses AI and machine learning for solar events. And he did most of the machine learning that I will talk about today. He built most of the algorithms, and he also dabbles in some helio as well. And then we have Mike, who was our facilitator throughout the program, and he is also an alumnus of the Frontier Development Lab. So now that I got that out the way, let's go on and talk about some science. So first of all, what are geomagnetic storms? What is space weather? What are energetic particles? Okay, so basically this is what's going on, right? We have events that happen on the surface of the sun that can be solar flares. It can be coronal mass ejections. We can have solar filaments, coronal holes. And from these events, we get things like solar wind or high energy protons that hurtle through the interplanetary medium and then meets us at our magnetosphere. And as you all know, it can cause damage to our satellites, International Space Station, to our humans in space flight, and then it can also pierce down past our magnetosphere, and then it can cause damage to our power grids, and it can also cause ground perturbations, where it's kind of like vibrations on the Earth's surface. And that is essentially what our group was attempting to do. We call it from the sun to the mud. So we are trying to create predictive models that can give us lead time for events that happen on the surface of the sun and to those ground perturbations. So what we need is we need actionable and operational forecasting pipelines to predict those geomagnetic fields in order to mitigate any damage that it may cause, which can run up to trillions of dollars. I've been on the National Public Broadcasting a couple of times because we are in solar maximum right now. Solar minimum is where we have, in the word, minimal amount of solar activity, but now we're in solar maximum where we have a lot of activity going on. And in the past couple of months, we've had some geomagnetic storms that have caused radio blackouts. And I had the pleasure on speaking on some of those things and on a couple of podcasts too, like ologies and stuff like that. So let's talk about what we have done before. So first of all, the Lagrangian point is where we have quite a few of our satellites that collects some of the data from solar wind and from high energy protons. We focused on solar wind. So in 2020, before COVID really hit, we started the Geo effectiveness group, and we started with the deep learning geomagnetic perturbation, also known as DAGGER. And what that machine learning algorithm does is it takes solar wind parameters from ACE and from Discover, and it predicts the geomagnetic perturbations on the surface of the sun, the supermag geomagnetic perturbations on the surface of the sun. And this gave us a 30-minute lead, which is better than nothing, but we definitely need more than 30 minutes. We won't be able to get in. I can't even drive in Atlanta traffic in 30 minutes. So then in 2023, the next team was the solar wind and high speed enhancements and transients handler, also known as sheath. And from there, we actually took it back. So we started from the magnetosphere, and then we took it back to the actual events that happen on the surface of the sun. So we took images from the Solar Dynamic Observatory, and we use those images in order to try to predict the solar wind outcomes. And then those outputs were the inputs for the DAGGER model. So we have two models. We have sheath. The input are the images from the Solar Dynamic Observatory, and then that spits out or outputs solar wind parameters that are then used as inputs into DAGGER, and then that will give us the outputs of the predictions for the geomagnetic perturbations. So, like I mentioned before, we have sheath, we have DAGGER. So then what about my group? So this past summer, we created Geo-CLoak, which is a forecasting pipeline that connects both sheath and DAGGER through real-time continuous learning. So real-time data is not actually it's happening and then we grab the data. No, near real-time data is about every 5 minutes, ACE and Discover drops some solar wind parameters, and then we pick that up and we automate that process into some data manipulation that then pushes into our machine learning models. What Geo-CLoak did was connect that. So we have near real-time images from the SDO that feeds into sheath, and then those outputs feed into DAGGER, and along with the inputs currently from ACE and Discover of the solar wind, and then that gives the outputs of the ground perturbations. And last but not least, we have live inference, which I really had to fight for. I am one of those scientists who genuinely believes that that science should be for everyone. We're using public funds, so the public needs to have access to anything that we're doing as soon as possible. So I created an application where you can see what we are doing live. Every 5 minutes there is an update, and I did the front end and the back end along with the database integration. So let's talk about the Geo-CLoak model suite. So like I mentioned before, we have images that are coming from SDO, and then we pre-process that in near real time, and then that goes into our DAGGER model. And then those are compared to the real-time solar wind parameters that are coming from ACE and from Discover. And then that predicts, that gives us a global prediction of the ground perturbations, along with uncertainty quantification using Gaussian processes. And then we drop it into our Google Cloud storage, and then that's where we pick it up inside of the live inference. All right, so let's go into sheath just a little bit more. So like I mentioned before, our images go through the Gaussian mixture model, and this is a process that begins with the application of Gaussian, and Gaussian is a statistical method used for identifying and modeling different clusters or groups. And in this case, in our case, we are trying to identify coronal holes and active regions. So solar flares and CMEs may come a little later, but for right now, we're focusing on coronal holes that gives us the most solar wind. And then of course, everybody who does solar physics mostly focuses on active regions. And then so from there, we use masking features and computer vision in order to extract those physical parameters from the coronal holes and the active regions. So basically, when it comes to computer vision, if you're not sure of it, what happens is we take the images, we grayscale them from 0 to 255, going from absolute black to white. And then we filter that through the images. And then we try to extract features based on the pixel intensity. So of course, if it's a solar flare, it'll be brighter, coronal holes are darker. And then from that, we turned those 26 quantifiable features into a vector that would then be pushed into our Dagger model. So the graphs that you see up here are the predictions of the solar wind that is coming from sheath. And you can see temperature, you see the density, and you see the speed. This is in time series. I'm not sure if you've heard of time series, but time series is basically where you're just tracking the events of something over time. So the time series models are pushed into our Dagger model. So we have one machine learning model, which is sheath. And now that is going to go into another machine learning model, which is Dagger. Now, before I go into Dagger, I think that it's important that I mention how insanely expensive this can get. Having one machine learning model can run you some bands. But having two machine learning models running at the same time continuously causes a ton of money. And this is the reason why Google Cloud and NVIDIA are both a part of this project, because we had endless funds. We just basically do what you need to do in order to try to make this work within 8 weeks. So we was like, hey, we can just connect them all together with Sheath as its own machine learning model, and then Dagger as its own machine learning model, and then we connect those. So let's talk about Dagger real quick. So the Dagger continuous learning model starts with a graded recurrent unit, which is a type of neural network to process data over time. And then we go to a fully connected layer where the data is passed through, different types of analysis in order to extract more features from it. And then we have the decibel measurements that come from the actual stations on the ground, which helps with our global forecasting so that we can do some validation. And then we have the output model from, we have the output of the global forecast that make predictions on the models. So now, we have, in machine learning, we always have issues with really just about everything. But I'm pretty sure that you've heard of the black box, where there is a lot of parameterization going on, a lot of back propagation going on, and it can cause some serious issues with our model. So when it comes to continuous learning, we have something that's called catastrophic forgetting. And this is a phenomenon where the neural network forgets previously learned information when it gains new information. And this is a serious problem when you're trying to do continuous learning, because we have our information pumping out every 5 minutes. Like as we speak right now, this project is still ongoing. It doesn't end until October 24th. So every 5 minutes, I have it set up on a scheduler to push out data. So we can't have catastrophic forgetting. I mean, well, we're going to have it, but we got to do our best to try to mitigate that. So the bar chart shows the progression from 2001 to 2024 in 3 stages, where 40% of the data is extracted from the previous stage in order to help the model retain user information from the past stage. So every stage that we have, we're taking 40% of that data and mixing it in with the new data in order to try to subjugate that catastrophic forgetting. Now, elastic weight consolidation is a technique that is used to aid for the catastrophic forgetting by adding in constraints that we preserve as important parameters, which is shown in the green. And then we have the no penalty areas, which is where you can modify the parameters with no issues, and you just do what you like. The ellipses in the extreme right visualize how the model's parameters evolve over time. So now I can't talk about anything dealing with machine learning without talking about the evaluation. So we utilize 3 evaluation metrics to assess the Dagger CL model. We use the mean squared error, we use the root mean squared error, and we use the mean absolute error. And these metrics were applied across all 3 stages of the continual learning, which gave us the comparisons between the training and the validation sets. And generally, there appears to be a trend where all the error metrics increase from stage 1 to stage 2, and then they decrease or stabilize in stage 3. So this pattern suggests that there are some improvements or adaptations in the model over time as it processes more data. Improvement is a very strong word to use when we're dealing with machine learning algorithms. It gave us results that we can use in the future, because this is still a work in progress. Continual learning is something that is fairly new to us. So we are in the learning process, but we have at least gotten some sort of decent news, is what I would like to say. Now, for all 3 metrics, the training data consistently show lower error rates compared to the validation data, and that is expected as the models tend to perform better on the new trained data. However, the presence of this gap indicates how well the model generalizes to new and unseen data. Now, the standard deviation bars indicate the variability of the model's performance. Notably, the variability tends to be consistent between training and validation phases, suggesting that our model is somewhat stable across the different data sets. So in conclusion, the observed reduction in error rates and stable variability by stage 3 suggests that the model could be effectively learning and adapting without overfitting. This is what we're hoping. The model, like I said, is still running every 5 minutes. So we'll, keep it updated as we go along. But as for right now, it looks like things are running smoothly. So our aim is to make predictions of global geomagnetic field perturbations via sparse supermag magnetometer forecasts. There are approximately 600 ground supermag stations spread across the globe. Most of them are in the Northern Hemisphere. And we approach this problem using a statistical learning technique called the Gaussian process regression. And this is a machine learning technique which assumes Gaussian noise and priors and a linear model. And we can therefore predict the global mean and standard deviation of each geomagnetic field component. As the linear model, we use spherical elementary currents, which is a physics-based model that mimics the ionospheric current flows. Now, I'm not exactly sure what was used before. I do believe that it was just linear models that were used before. We moved over to using spherical models, which makes sense because we're on a sphere technically. So we definitely got better results by changing it from a linear model, using the spherical elementary currents. And after rigorous comparison with other models, we found that the spherical currents are the most accurate. So overall, we were able to do some sort of predictions of the global geomagnetic field perturbations with quantified and reduced uncertainties. And that leads us to the web application. So this is how it looks. we have the about section, which talks about every single group that we've had. We have sheath, and we have dagger, and then we have the data sources. Geo-CLoak provides actionable forecasts of global ground geomagnetic perturbations, near real-time online inferences. And I think that what we have is definitely something that is fit for the future continual learning framework that we have set up for FDL. Now, I do want to go a little bit deeper into the things that I was a specific lead on. I do quite a few things when it comes to software. One of my degrees is in computer science, and I build software from scratch. I make video games from scratch. I really do everything from scratch. So I was tasked with data extraction and storage for near real-time information coming through the pipeline. And I just wanted to show you all the architecture that I built and the services that was used in order to make this thing run efficiently. So we take the information from NOAA, and we do that by creating a Google Cloud function that sits inside of the Google Cloud platform. And then you have a scheduler that you set up that basically is an API trigger that triggers the function to basically call the function. So every 5 minutes, call this function. And then that function picks up our SolarWind information and our SDO images, and it drops it into the Influx database. And that is updated every 5 minutes. Now, on the other end, when it comes to the application that I made, I used a language called Python. I used a library, well, quite a few libraries, but the library that was used in order to make the web application is called Streamlit. And that was pushed to the Google Cloud build, and then Google Cloud Run dropped into an artifact registry. And then that was pushed onto a Docker container that is then displayed to the user. So our machine learning models sit on separate compute engines. So we have engines for Dagger and for Sheath, and then that information is pulled in real time into the application. So this is how the Influx database looks. This is what I set up. And you can see time series happening in real time. And how long has it been? About 20 minutes. Yeah, that's it for me. Thank you all for listening. And I'm open to any questions.
Okay, that was such an awesome talk. I have so many like things I wrote down. Thank you so much, India, for that really cool, amazing talk. So this is our portion of the series where if you have any questions, hopefully you'll be able to drop them in the Q&A, and I'll either read them to India, or we'll get the questions to her to be able to answer any questions you have, whether it's regarding things that she talked about in her talk, things that you would like more clarification on, or just general things about like her journey in the field, or she's open to any of those type of questions. Let me see. So yeah, so we have a couple. I'll ask those first, and then we have time. I'll get to my own questions. I wrote down like 6 of them. So it was so cool. So the first one is from Josh Jasper. It says, "Thank you for sharing." The question is, what do you see happening after this project ends in October?
Well, for me, or so for the project, as in the longevity of the project, or for me?
Maybe perhaps both. I'm not sure that there wasn't any
Okay. So for this project, continuing this project really depends on the results that we get, right? So My team presents October 24th. We are still working on it. Everything still looks good. And if our algorithms show real promise, then it will be transferred over to the next summer, because this is a summer postdoc. And hopefully, I don't know, maybe I could be a faculty member next summer. I don't know. We'll see. But I do think that this has promise. I do think that this will continue to move on, because we do have different levels for all of the projects within FDL. And I do think that our project was substantial enough to pick up where we left off, and to continue to try to make the model better. Because I mean, when I say this stuff is expensive, I mean it. So they probably will shut down everything on October 24th, because it's really eating up money. So then the next team will have to come in and then basically try to push all of the data from October to next summer in to start the project over. So I do see this project moving forward in the future. Now, as for me, I do enjoy continuous learning. I do think that I may venture into this a little more in the future. As for right now, is a postdoc. That's for me right now. I'm trying to make sure that I solidify a position to continue to do research. Okay. And then I'll be able to do what I can dibble and dabble in some other things. But as for me right now, I'm headstrong on postdocs and teaching at my HBCUs. So
Yeah, and for folks that are listening or watching this recording later on, and you're hiring, please get in contact with Insta. Like, she's so awesome. Like, y'all are going to be missing out. Okay, so thanks for answering that one. So our next question comes from Anusha. She says, "Thank you for the really fascinating talk. Your discussion of catastrophic forgetting stuck out to me, because I would expect more recent solar data to be a stronger indicator than older data. Did you/your team investigate how far back data from the past needs to be preserved for effective prediction, and if there is a point where you get diminishing returns from trading over more data?"
Short answer, no, we have not done any research on that. This was a summer 8-week project. We had to push through and get things done. Have we talked about this? Yes. Will future teams work on this? More than likely, once we tie up the bow of geo effectiveness, because we're really towards the end. So I would say at the most 2 more summers. But to answer the question bluntly, no, we have not thought about. Well, we have thought about it, but have we implemented anything? Have we done anything to try to mitigate that? As of yet, no. We're just trying to make sure that the framework works, since we're the first team that is pushing out continuous learning or continual learning. And catastrophic forgetting actually is something that came up because we noticed that it was forgetting, and we was like, what the hell is going on? So, well, we was like, okay, well, we know that this is going on. Do we know exactly why? We're not sure. It definitely has something to do with the past data, but we're not exactly sure why. I know we got 5 weeks left, so we got to move it along. So I'm sorry I couldn't give a better answer.
No, that was great. So we have another question. Someone says, as someone who helps fix issues in the Google Cloud every day, how easy did you find it to use as a potential first-time user for this particular use case?
That's a great question. I started with Amazon Web Services, and they're very similar. So with already having cloud experience, it was really like like if anybody out there who's listening has learned any computer programming languages, once you learn a couple of them, you can really pick up on just about any computer programming language. And that's how it was for Google Cloud Platform. Since I have so much experience using AWS, because I use AWS for my dissertation. I was able to be very interdisciplinary at Georgia State, and I made software for my dissertation, and I use Amazon Web Services. So, I mean, they're all very similar, you know. You have Google Cloud Functions, you have Amazon, you have AWS Lambda, you have APIs on both ends, you have buckets in AWS, and you also have buckets in the cloud storage. So, doing that transition from AWS to Google Cloud, the only thing that it did was made my CD look better, because baby, I was able to pick up on that. And I don't want to say that I like it better. They're different. I know how to use both, but I do like Google Cloud because there's a lot of things that you can do because Google is a part of our everyday lives. So, you know, like with the maps and all that stuff that I can incorporate with things. So yeah, it wasn't that hard of a transition for me. For my teammates, I'm not sure. But I definitely use the Google Cloud services the most. I use a ton of them, as you can see from my last slide.
Nice. Thank you. Okay, so this next question from Jordan says, hello, hi, great talk. I'm thinking about the solar cycle and the baseline you have for the neural net. When you're doing the machine learning processes and bringing in new data, have you seen any changes in solar properties / effects that move with the solar cycle, or is this data set more of a proof of concept?
Yeah, it's definitely more of a proof of concept. Now, what was just mentioned is something that we have also talked about, how that data changes along with the solar cycle, and that will be fun to dig into deeper. Really on my own, I would like to see, I mean, I love patterns, I love numbers. I'm a mathematician first. I have 2 degrees in math. So I'm a mathematician first, and I would definitely I was definitely interested in how those numbers and how those patterns change along with the solar cycle. But unfortunately, no, we didn't go that deep into it. But that is a good question to bring to my teammates when we meet on Monday about
Period.
how that about how the solar cycle may be affecting the data, our outputs, and then back to the catastrophic forgetting, how all of that is interconnected with the solar cycle.
Nice. And this next question, you might have touched on it a little bit. They said, thank you for your time today. What was your favorite part of developing this project?
Um, the web application was fun, but I've been doing that since I was like 12. So I would say the most fun part was obtaining the near real-time data, doing the manipulation, the data mining, and then storing it, and then creating functions, and then creating schedulers that picks it up and drops it into the database in real time. That was the most fun part for me because that was something new that I haven't done before. I thought that it was the most, and I think that what we do in Astro is beyond amazing and cool. That will never change. So I think that it is amazing that we have access to our satellites every 5 minutes, that we're getting that data in damn near real time. Like, this is ACE, this is Discover, and they are data streaming down here, and we're getting information every 5 minutes directly from the source. And I'm able to manipulate that and move things around and put it into a place so that people can use it. So like I mentioned before, the biggest thing about me is access to the public, and being able to create platforms, or being able to create applications so that everyday citizen scientists can get access to it is what's most fun about being a scientist to me. So that was the most fun part. Creating a database that is public, by the way, that runs so efficiently, and it's automated. You know what I'm saying? Like, that's another fun thing that I absolutely love, is the fact that I know how to automate things. So as I'm speaking right now into this camera, and everybody that's listening, I created things that are running in the background seamlessly to make things move and to make things work. So that was the most fun for me. Web application will always be fun. Building web pages and video games and stuff will always be fun, but that was the best part for me.
That's so cool. I'm so in awe. You said something about like doing stuff since you were 12. I feel like I was just leaving making like mud pies in the ground when I was 12, and you're like building
Girl,
stuff.
no. I just my parents were very young, but they always made sure that we had everything that we needed. So my daddy got me a computer, and I just turned 38. So, it was AOL and Black Planet and MySpace. So back then you had to know a little bit of HTML in order to make your, page pop. So I just took to it like it was nothing, and took a class in high school my senior year on building web pages from scratch, and I took that along with me all the way up. I was a webmaster of the math club, and it's always just been a hobby. And then I was like, hey, I'm already taking some computer science classes as I finish up my PhD. I might as well get the master's, child, because it's free. So I might as well get the master's in computer science. And my advisor was like, do it. So I was like, okay. So I took my last little few classes. I got my master's degree in computer science along with my PhD in astrophysics. And yeah, so it's always fun building applications, but I know how to do that. You see what I'm saying? Like, I know how to do that. But baby, grabbing that data in real time like that and then setting all that stuff up, I was like, oh yeah, I am that girl. I am her. She is me.
It's amazing. Okay. So I actually had a few questions myself. I think we'll continue with questions for maybe another 10-ish minutes or so. So if people have more questions, please feel free to put them in a chat. But I want to be a little selfish and ask someone some questions that I had because your talk was really awesome. So one of the questions that I wanted to ask, you might have touched on this a little bit, is so it's kind of a two-part question. The first one is do you see or where do you see people that are interested in like that are citizen scientists to come in and possibly work with this data or with this project? And my other question is a little related to this, but I'm also really interested in, once we are able, to possibly like predict these kind of this solar activity ahead of time, like what what happens what happens after that? Are you like kind of in the realm of like okay, something's big coming or something, like what do we do? Like what do we do now? So those are kind of the two questions that I wanted to ask.
In terms of citizen scientists, um, they're really everything is already public. Well, not everything. Most things are already public, right? Like the data that we're getting, even that is public. And the database that we created that will be public. But as far as citizen scientists being able to collaborate with this project, I ain't got no say so in that. I mean, it's only so far that we can go when it comes to these type of partnerships with FDL and NASA and Google and NVIDIA. They are very strict with some of the things that they choose to do. Now, in terms of me personally as a scientist, that was one of the biggest things that I put inside of my postdoc proposal is working with citizen scientists. There are geniuses that are out here that have not gone through the academic process, that don't want to go through the academic process, that also needs to be able to contribute to science. So I am very big on that. Everything that I do is I simultaneously think of the public at the same time. So I build applications as I do the research. I build the applications so that people can have access to it. And I definitely want to work with citizen scientists in the future, with credit and everything. Now, if there are any citizen scientists that are listening right now, I do believe that NASA does give funds specifically for citizen scientists. You would need to go on Inspires, I think, and type in citizen scientists, and they do have funding for citizens to conduct science using the data that NASA puts together. Now, the other question that you had was, what are we going to do after we give the announcement that something happened? Go in the house. Let me tell you something that I learned, okay? The hard way, okay? Since it's Black in Astro, let me tell you something, okay? I am from Georgia, Atlanta to be specific, okay? And you couldn't tell me that I would ever sunburn. You understand? I'm Black. I don't sunburn. I ain't gonna sunburn. I ain't gotta worry about that until I went to the Bahamas. And I came back and my back was peeling off. It looked like port rinds. Okay. I have to wear sunscreen now. So when events like that happen, or if we know if we have a lead time, and try to stay in the house, stay somewhere where it's cool, put on sunscreen if you have to go out. We have to have things in place for like power grids. And when during my last NASA internship with the heliophysics space mission design school, that program, by the way, was beyond amazing. And it teaches you how to build grants in order to put instruments into orbit. So what I learned there is that they actually do have a heliophysics division that mitigates those satellites from getting all of that damage. And I think it was aluminum, simply aluminum, that they use in order to protect against high energy protons. But basically what I'm saying is ain't nothing we can do. Like this hurricane coming through Georgia right now and everybody going crazy, ain't nothing we can do but stay in the house and just wait for it. It's weather. You know what I mean? Like ain't nothing you can do. Put on some sunscreen and sit in the house.
I hear
Just
that.
let you know that it's coming. We just letting you know that it's coming. So
That's fair. That's valid. That's fair. That's valid. So, so I'll ask one other question and we'll probably wrap up a bit. But one of the things is Trinity, you say you popped in a bit late. Yes, this will be like recorded and put up on the YouTube for Black and Astro. So don't worry about that. You'll be able to see that as well. So my next question, and sorry if it's a little naive or totally not related to any of this stuff, but can I study a lot of like I study like exoplanets and different things like that. So I didn't know, my question is kind of a two-part question, is that the sun is right there, right? So could this same technique or pipeline or anything be used in exoplanet science for like M dwarfs, whatever, to predict weather as it pertains to like maybe how it's impacting close in like planets and stuff, as we think about habitability or things like that? Or we're still very in like the early stages of this, is more applicable to like sun-like stars, or does it not particularly matter the type of star? Does it just needs to be like pretty close or things like that?
Basically what you said is that more so I'm a heliophysicist, so that's the sun and within our heliosphere. So the only thing I can tell you is that I know that this works for sun-like stars, G stars.
Yeah.
And middle-aged G stars with habitable zones is all that I know thus far. Now, could this work for other stars that are like our star? Probably. But I can't tell you definitively. I just focus on the sun part of the astro, just our star. But space weather is space weather, gamma rays, x-rays, radio waves coming from a star. That is what space weather is. It just so happens that we have this star and we are on this planet and we are within this habitable zone. But even outside of the habitable zone, right? There are heliophysicists that study space weather for Mars, that studies space weather for all of the other planets because it's within our heliosphere. So could this pipeline into future stars? Yeah, I could definitely see that. Some of the techniques used, things will have to be changed, of course, because hell, we better know what's going on with our star, But how does the plasma, works? How does the magnetic field works on these different types of stars? I'm pretty sure that it's different from our star. So I really couldn't tell you, but that's what's fun about science, is that we don't know, but we can find out, can't we? We can try. We can try to find out. That's the point of science. That's why I love it. You ain't got to know everything.
Exactly. Okay, awesome. So there's one other question in the chat, And then so I'll ask this question, and after this question, you answer it. And then if there anything you want to share with people about ways to get in contact with you, other things you're looking for in the future, and then we'll go ahead and wrap up. So the last question is like, just how and where can we access the data?
It will be available after October the 24th, and it should be available on our web application. And I will share that with Caprice, and I'll probably put it out on my socials as well. And FDL will probably put it out too. So if you're not following Frontier Development Lab on LinkedIn, follow them. They give updates all the time. I will post it on my socials. I'm on all socials. I will have I will ask Black and Astro to post it as well, so that you can get access to the data, to the application, so that you can see what's going on, because we do need for applications to we need more applicants for FDL. I don't know. Quite a few people are terrified of applying for fellowships that include machine learning and AI. You don't have to be perfect. It is a learning process. So I will definitely get out all of the information. I will give all of the information to Black and Astro, because it's a shame that I was the only Black face there. We need more Black faces in those spaces. Especially in AI as a whole, we need more Black people to interact with that, so that we'll have less biases in some of these things. So don't worry, I will get the information out there for everyone.
Cool. Thank you. And then the last part is just like your red carpet moments or anything you want to promote, like say like where people can find you online, or ways to contact you, or general things you're looking for, whether it's jobs or little things like that. I'll give you some time to kind of red carpet yourself.
Well, I mean, you can just go to Google. If you type in India Jackson, I should pop up. I have Twitter, I have LinkedIn. I also have a Facebook. If you still, I know people ain't on Facebook no more, but I'm a millennial, so I'm on Facebook. Okay. I was in college when Facebook started. So I was where you had to have a .edu on the end. Okay. So Facebook ain't going nowhere for me. But that's where you can find me. Like I mentioned before, I am in the process of applying for postdocs. I have applied for a postdoc. If you believe in a higher power, please pray for me that I get this NSF postdoc, because I really need it. After a PhD is really the hard part, because you have to get work, and a lot of we are so busy in the middle of a PhD that we tend to forget about afterwards. So I'm hoping that I get this postdoc where I can continue my research using AI and machine learning and heliophysics and building software. And yeah, that's about it. Thank everybody for listening to me. I appreciate it.
No, thank you for such an amazing talk and great Q&A. So with that, we'll wrap up here. And as I said, this is recorded and we'll upload it to our YouTube at Black and Astro soon. So thank you again, India. This was amazing, and I'm glad you could be the very first speaker for our speaker series.
Thank you. It's an honor. I appreciate it.
Of course. All right. Thanks, everybody. All right. Bye.